Swayam Prabha. Digital India. Educated India.
Let us look at a different kind of problem. We have seen stepped shafts with some condition on the comparability condition. Okay. This condition, the delta C is delta, small delta is a comparability condition. Okay. Next, let us look at a composite cylinder. Say I have a steel pipe filled with concrete. I have the steel pipe filled with concrete. Okay. This is concrete, this is a rigid plate. I have two rigid plates on top and bottom. And I am subjecting this to a compressive load P. Okay. So, I have a steel pipe filled with concrete and I am subjecting it to a compressive force P. Now, I want to find the stress in steel pipe and concrete. Okay. Now, how do you go about solving this problem? The systematic way is to assume some displacement field, to compute based on the displacement field the strain. From the strain you compute the stress using the constellation, then use the equilibrium equations to relate it to the applied force P. Okay. So, what is the possible deformation for this composite system? The plate can move down like this. This rigid plate can move down like this by an amount delta say, and I am assuming that this is fixed on the ground. So, this does not move. Okay, I am assuming the top plate alone moves down by an amount delta. So, what will be the, and let us assume that the coordinate system is given by this. The coordinate system is given by this orientation x and y in the plane and z along the axis of the cylinder. Okay. Okay. Then what will be the stress state? What will be your sigma and what will be your epsilon for this deformation? That is the question. Okay. Since I am applying a force along the z direction, there will be stress sigma zz alone, and let us assume for the moment that the stresses in other directions and other shear and normal stresses are 0. Okay. This will not be true when the Poisson's ratio of steel and concrete are different. In fact, the Poisson's ratio of steel and concrete are different, and hence the stresses in the other directions will not be the same, will not be 0, but we are assuming that they are 0. Okay. Now, what will be the strain corresponding to this? It has displaced, the top plate has displaced by amount delta. So, strain roughly is the change in length by the original length or displacement delta divided by L, as we saw in the case of a uniaxial member. Here it is compressing along the z direction and hence the strain is along the z direction, and then there will be Poisson strain in the other two directions, which for now we will ignore. We will ignore these Poisson strain, there is no shear strains. So, we will ignore those strains. Okay. Now, what happens is the stress and the strain are related through the constellation. Now, sigma ZZ is E times epsilon ZZ, right. Okay. This is broadly if the member were to be made of the same material, but I have now the body made of two materials. Okay. So, what will happen? I will have epsilon ZZ of concrete will be equal to epsilon ZZ in steel, which will be equal to delta by L, because the plate is rigid, there is no rotation there for the steel and concrete to have different strains. The rigid plate moves as a rigid plate and hence the strain in the steel and concrete would be the same. Okay. Now, since the strain I have computed the strain, so next I compute the stress in the concrete would be E of concrete times delta by L, the strain in the concrete, and sigma ZZ of steel would be the Young's modulus of steel into delta by L. Okay. Now, what should I do next? Appeal to the equilibrium equations. Equilibrium equations is the force in the concrete plus force in the steel, the axial force Fg in the steel and Fg in the concrete should add up to give me the force P, because my rigid plate has this force P coming in there and there is this force F steel and there is the force F concrete. Okay. So, these forces should add up to the applied force P. Now, what is force in concrete? Force in concrete would be the force in the concrete would be the stress in the concrete times the area of the concrete. Okay. So, basically from there I get that this implies E concrete into area of concrete into delta by L. This is the force in the concrete plus the force in the steel, which will be E of steel to area of steel into delta by L must be equal to the applied force P. Okay. Now, from here I get what is delta. From here I get delta to be PL by area of concrete to Young's modulus of concrete plus area of steel into Young's modulus of steel. Okay. So, I have found what delta is and related to the applied force P. Okay. So, what are we interested in mechanics? Relating the force to the displacement. So, given a force P, I know what will be the displacement delta here now. Okay. But what I am interested in this problem? I am interested in finding the stress in steel pipe and stress in the concrete pipe. So, coming back to the expression for the stress in the concrete. So, sigma ZZ of concrete would be E of concrete into delta by L. So, that will be P divided by area of concrete to Young's modulus of concrete plus area of steel into Young's modulus of steel. Similarly, sigma ZZ of steel would be Young's modulus of steel into P divided by area of concrete, Young's modulus of concrete plus area of steel into Young's modulus of steel. Okay. So, this will be the state of stress in the concrete and the steel pipe. Okay. On the other hand, if I were to consider the differences in the Poisson's ratio, what will happen? that is the question next that we want to consider. If I were to consider the Poisson's effect, what will happen? The strain delta by L here will result in a strain of minus mu delta by L, and here it will be minus nu delta by L, right. Now, since the Poisson's ratio is different, but delta by L is same, what will happen is the concrete will expand differently from how much the steel expands. Okay. So, there will be a interfacial stress that develops between the concrete and the steel. Okay. So, in that case the free body diagram for this member will become this is a steel pipe, there will be some inner pressure Pi acting here, the steel, okay. Added to that there will be sigma Zz acting along the circumference of the steel pipe, there will be a sigma Zz circumferential stress acting along the axial stress acting along the circumference of the steel pipe to sigma Zz, and in the concrete the concrete pipe, there will be the counterpart of this Pi, Newton's third law coming into effect. This concrete cylinder will be subjected to a external pressure Pi, okay, and it will also be subjected to an axial compression along its circular cross section, which is sigma Zz of concrete. Sigma Zz of concrete, this is sigma Zz of steel. Okay. Now, the state of stress is no longer uniaxial, it is biaxial to say the least, if not triaxial. Okay. So, basically you have to know then how to solve the problem of an annular cylinder being inflated or a solid cylinder being deflated, okay, to be able to solve this problem. We will come to this full solution of a 3-dimensional inhomogeneous axial member later in this course. Okay. All that I want to say is this solution that sigma Zz of concrete is E of concrete times the applied load divided by E of concrete into area of concrete plus E of steel into area of steel and so on, applies only when you make the assumption that the steel and concrete have the same Poisson's ratio, or ignore the second dimensional or third dimensional effects of the body. You are interested only primarily in the axial deformation of the body, then only these expressions will hold. Okay.